Hey everyone, welcome back. In this video, we'll introduce the normal distribution, which is one of the most commonly used continuous probability distributions, both in theory and in practice. So let's jump right in. We'll start by talking about the properties of the normal distribution and how we will find probabilities associated with this normal distribution. We'll also introduce a rule of thumb for finding normal probabilities in normal ranges in a fast way called the empirical rule. So let's start by defining the normal distribution. The normal distribution looks a little bit more complicated compared to the distributions that we're used to working with so far. We say that a random variable y follows a normal distribution with parameters mu and sigma if the density function is 1 over the square root of the quantity 2 pi sigma squared times e raised to the negative y minus mu squared over 2 sigma squared. This distribution exists for any real valued mu and any sigma greater than 0. We then say that y is distributed normally with parameters mu and sigma squared. So in that shorthand notation here, the value of sigma that will be reported is actually usually sigma squared. The normal distribution has a very familiar shape. Another term for this distribution is the bell-shaped curve. Right away we can see how this normal distribution changes depending on its parameters, depending on the values of mu and sigma. So this parameter mu seems to indicate the center of the distribution, or where this distribution peaks. Right around, for example, -1 with this coral line is the peak of this normal distribution. Now look what happens as we increase that sigma squared parameter, going from green with the smallest sigma squared to blue to coral. The higher the sigma squared value, the more spread out this distribution becomes. So that should give us a little bit of a hint about what that sigma squared parameter represents. Now let's talk about the form of this PDF, or this density function. The integral of f of y for a normal distribution has no closed form solution. So what that means is that we won't be able to integrate in order to find probabilities related to a normal distribution. Now we can certainly use numerical approximation, and in the past that is what was done. The way that we would use these numerical approximations is to build a table of normal probabilities and then look up values in the associated table. Not the pleasantest way to find them. So we'll use our functions to help us out here. The same basic structure of prefixes indicating the type of probability calculation, suffixes indicating the distribution. Here we'll use a norm suffix. There are two parameters for these functions. We'll need to report the mean of the distribution. We'll also need to report the standard deviation of a normal distribution. So where we get those mean and standard deviations come from the parameters themselves. Like we suspected from the plot, the mean parameter is represented by that mu. The variance is represented by sigma squared. So in order to get the standard deviation, we'll simply take the square root of sigma squared. So let's find some probabilities related to this normal distribution. We have a normal with mean 2, variance 9. So sigma squared, or standard deviation, of 3. So in order to find cumulative probabilities, or probabilities up to a particular point, we'll use the p prefix. So for example, to find the probability that y is less than 0 from this normal distribution, we'll take p norm, we'll enter in 0 for our desired cutoff argument. Our mean is 2, our standard deviation is 3. So this gives us about a 25% probability within that region. The probability that y is less than 2, the normal distribution is symmetric. If 2 is the mean of that distribution, the probability of observing a value less than the mean must be 1/2. The probability then of finding a value less than or equal to 2, I apologize, there is a typo here. Our argument should still be 2, not 0. The probability less than or equal to 2 should be exactly the same as the probability less than 2. Why? Well, because this is a continuous distribution. So we're not assigning probability to any one point in particular. Let's look at a few more examples. If we want to, say, find the greater than probability, so find the probability that y is greater than or equal to -1, we'll then do 1 minus the p-norm function. To find the probability that y is less than 5, we get pretty large, 0.814. And then finally, let's talk about how to find probabilities related to ranges with the normal distribution. Now, none of these helper functions that we've been using in R can accept a range sort of output. You can certainly input multiple values into, say, p-norm, for example, but what you'll get are multiple cumulative probabilities. You won't get the range in between any two numbers. So in order to find, for example, the probability that y is between some range, say -1 and 5, what we can do is take the probability that y is less than 5 and subtract away the probability that we don't want, specifically the probability that y is less than -1. So that gives us about a 68% chance that y is between -1 and +1. So let's take a look now at another type of normal probability calculation. Let's say that we want to find quantiles associated with the normal distribution, or the cutoff for a particular level of probability. In order to find those quantiles, we'll use a function called Q-norm. So for example, if we want to find the cutoff that gives me the lower 40% of this distribution, we'll use the Q-norm function. Our input argument becomes 0.4. And it turns out that there's a 40% chance, or a 40% probability, that y is less than 1.24. If we want to find even smaller probability cutoffs or even larger probability cutoffs, we just change that argument that goes into Q-norm. So for example, 10% of the observations in this distribution will be less than -1.84. 99% of observations from this distribution will be less than 8.98. Here are some more examples of how we can work with this. So let's say, for example, that we want to find the cutoff for the middle 80% of this distribution. We want to find the values that envelop the middle 80 of the bell curve. Well, if there's 80% in the middle, that means there's 20% left over, half on each edge. So we'll need the 10th quartile, or the 10th quantile, and the 90th quantile, or the 90th percentile. So 80% of the observations in this distribution will fall between -1.84 and 5.84. If we want the 50th percent range in the center, we'll need the 25th percentile and the 75th percentile. So half of the observations will be between -0.02 and +4.02. Again, taking advantage of that known symmetry of the normal distribution. Okay, so we've gotten some practice just working with that normal family of functions in R. Let's go ahead and apply this to some problems. So let's say that the final exams in a physics class will be scaled according to a normal distribution with mean 75 and standard deviation 10. What proportion of students will score between an 80 and a 90 on this physics exam? Well, in order to find this, remember that we need to take advantage of those cumulative probability functions in R, so we'll break this up into two basically CDFs. So the probability that y is between 80 and 90 is the probability that y is less than or equal to 90 minus the probability that y is less than or equal to 80. We'll calculate those two using the p-norm function. We get a final answer of 0.24. About 24% of students in this class will score between an 80 and a 90 on the final physics exam. Let's take a look at another example. The normal distribution is often used in manufacturing processes to sort of describe the variation from run to run of a particular process. So we have a production plant that is making ball bearings with diameters that are normally distributed with mean 3.0005 inches. So the precision here is out to about 4 decimal places, and standard deviation 0.001 inch. Our specifications require this ball bearing to be a very particular size. It must fall within 3 plus or minus 0.002 inches. If it's too small, it will fall out of the joint. If it's too large, it won't fit in the joint. So we need to be very precise with the size. Those ball bearings then that are outside this range are scrap and will be discarded. What fraction of our total production should we expect to fall outside of specification? So we have our range here, or our tolerance interval. We will scrap anything that is less than 2.998 inches in diameter and greater than 3.002 inches in diameter. So because those are disjoint events, we can break them into 2 different parts of this normal distribution. Using that p-norm function, the probability that y is less than 2.998 is very small, 0.006. It's more likely that if a ball bearing does not meet specifications, it's actually a bit too big. Using 1 minus p-norm, we get the probability that y is greater than 3.002 to be about 6%. Adding those 2 probabilities together, we get about 7% of ball bearings will be either too small or too large and need to be scrapped. Let's take a look at another example. The GPA of a large population of college students follows a normal distribution with mean 2.4, standard deviation 0.8. Whenever I specify this normal distribution, I will make sure to write mu and either sigma or sigma squared, specifically so you know whether or not we're talking about the standard deviation or the variance of this distribution. So what fraction of students will have a GPA greater than 3.0? Suppose that at this institution, students with a GPA less than 1.9 are put on academic probation. About how many students will go on probation? So we will start by saying that we know that GPA is normally distributed with mean mu, standard deviation 0.8. Using the p-norm function again, the probability that y is greater than 3 is 1 minus the probability that y is less than 3, so about 0.226 for our answer there. The probability that a student at this school will go on academic probation will have a GPA less than 1.9. We take p-norm 1.9, mean is 2.4, standard deviation is 0.8. We get about 27% of students at this particular institution going on academic probation in a given semester. Now let's take a look at some tools we can use to help us describe normal distributions. One common tool that can be used to compare one distribution to another is the standard normal distribution. We get that standard normal distribution from something called a z-score. So in order to calculate a z-score, do notice the typo here. The z-score is just y minus mu over sigma, so ignore the x at the beginning here. What we do is take our observed value, subtract the mean of our distribution, and divide by the standard deviation. Here's what that can do for us. This allows us to better compare values from 2 different normal distributions. Furthermore, we can think of this z-score as a unit of measure for distance from the mean. Again, in the formula where you see x, y, that should be y alone. So let's let x be a normally distributed function with mean mu, variance sigma squared. We can say that for constants a not equal to 0 and some other constant b, the variable y equals ax plus b, so a linear function of a normally distributed variable, is itself normally distributed. In order to find the mean, that expected value of y is just a times the expected value of x plus b. The variance of y is a squared times the variance of x. So if we make any sort of linear transformation on a normal random variable, we will get a normal random variable back. So let's use that to figure out how z-scores themselves are distributed. So z-scores, we can think of an observed value, say x minus mu over sigma. We can write that as really a linear transformation. So this z-score calculation is the same as taking 1 over the standard deviation times an observed value minus mu over sigma. Find the expected value of this. We get 0 for the expected value of a z-score because the expected value of y, again this x should be a y. This expected value for the distribution is mu. We get 1 over sigma times mu minus mu over sigma, or 0. Our variance becomes the constant a squared times the variance. So 1 over sigma squared is, 1 over sigma squared times the variance sigma squared, we get 1. We know that z-scores are also normally distributed because they're a linear function of a normally distributed variable. So this gives us a new normal distribution with mean 0, variance 1, that we'll call the standard normal distribution. So the standard normal distribution looks like this. It's centered at 0. The standard deviation size here kind of tells you how spread out this distribution is. For example, looking at this density function, the probability drops off fairly quickly once we hit about a standard deviation of, a distance from the mean, unit 2, -2, or +2. Once we hit about 3, this density function is almost 0. So we've really contained almost everything in a standard normal within 3 units from the mean. So let's find some probabilities associated with this standard normal. Let's find the probability that z is greater than 2. Let's find the probability that z is between -1.5 and +1.5. And let's find the probability that z is between 0 and 1.73. Starting with the probability that z is greater than 2. Because this is the, quote, standard version of the normal distribution, we can actually make our lives a little bit easier here. Notice that if I write p norm of 2 versus p norm of 2 and specify the mean and standard deviation, I get the exact same value back. What this tells me is that mean equals 0 and standard deviation equal 1 are the default parameters for this function. So unless we tell it otherwise, the normal functions in R will use mean 0, standard deviation of 1. On your own, try to write a function for parts 2 and 3. Okay, so based on this standard normal, we get a nice rule for working with the normal distribution called the empirical rule. And here's what this says. This empirical rule tells us that about 68% of the observations in a normal distribution are between the mean plus or minus 1 standard deviation. About 95% of the observations in a normal distribution are within the mean plus or minus 2 standard deviations. And about 99%, or almost everything in this distribution, are between the mean plus or minus 3 standard deviations. So if we're in a situation where we can't, for example, calculate normal probabilities directly, we can come up with some rough rule of thumb ranges with the empirical rule. So we can use the standard normal distribution to help us verify this. So for example, if I calculate the exact range between a z-score of -1 and a z-score of 1, I get a probability that is about 0.6826895, roughly 68% as a nice rule of thumb. If I do the same for plus or minus 2 z-scores, I get 0.954497. So again, pretty close to that 95% in our rule of thumb. So what value of z is going to satisfy that 0.95 directly? So here, for example, we used 2. We overshot just a little bit. Our range was slightly higher than 0.95. So if we use, say, the Q norm function, we can figure out what that exact cutoff is going to be. It turns out that exactly 1.96 standard deviations below the mean, 1.96 standard deviations above the mean, give that 95% probability. Now in the empirical rule, we want something that is quick, easy to remember, easy to apply. So that's why we round from 1.96 up to 2. Okay, so let's take a look at one result related to adding normal random variables together. So let y1 through yn be a sequence of independent normal random variables, each with a potentially different mean, say mu sub k for yk, potentially different standard deviation as well, sigma squared sub k for yk. It turns out that if you add these normal distributions together, their mean is just the sum of the mean. The variance is the sum of the variances. Now notice we're not multiplying any constants here. These are all the individual random variables on their own. If we did multiply by a constant or add a constant, this would change. But the takeaway point here is that the sum of normal random variables are normally distributed. So let's take a look at a result that follows from this. I'm going to define y bar as the sum of y1 up through yn divided by n. In other words, y bar is my sample mean, or my sample average. Suppose that y1, y2, all the way up through yn are identically and independently distributed. So they all have the same distribution, same mean, same standard deviation, and they're all independent of one another. They might not be normal. We haven't made this normality assumption yet. Let's find the expected value and variance of the sample mean. Again, we're not making any distributional types of assumptions. Well, how would we solve this? Well, we would find the expected value by applying our properties of expected values. Try to solve this one on your own at home. Let's add an additional constraint here. If it turns out that these are normally distributed, we'll get a pretty neat result. Think about these on your own at home. We will cover them in class this week, and I will see you then. Have a great day.